when we put this software together, one of the challenges we were tasked with is said, well, where are the users going to get this information to put in? You want to be probabilistic. We thought it's a really good question. So we had some effort over time to start building some of the information so it's right there embedded in the GUI that one could down select right from a drop down. We realized this is a big issue, right? I mean, to try to characterize probabilistically material properties for all the ones that we may want to use, that's a massive task. So we obviously are open to, if you have new sources of information, you have new publications, really, please, it'd be great if you would send that to us so we can roll that back into what we have got so far, and then we can roll that back out in the next version. Of course, use your own, as we said, and you can modify easily what the GUI has. So this is a big issue, but we wanted to see how far we could get. So we have a number of things, good sources that we pulled together from the public domain that we've embedded in the software. So let me just give you kind of a snapshot overview. I mean, we could have a whole afternoon just on how to do this and what's in here and so forth, but let's just have a conversation on it, at least. So we wanted to have a database of probabilistic data that you can then access from inside the graphical interface. Now, as you've seen, there's a menu-based selection, or you can type in your own right within, say, the graphical interface, select and put in your parameter values and your distribution type from the list that we have available. If you think the distribution would be best fit by a type that we don't have, obviously you can use tabular if we have that capability. If not, please let us know, because we don't always know what capabilities users need. So that's what we need to hear back from you. Number of data sources we've used. MMPDS is a great source. In the last free version we have used, obviously there's a paid version now that's proprietary, so we only used what was the last public version. Any papers we've had, there's some NDE capabilities books that have been funded by the government, that's in the public domain. Damage tolerant design handbook, a number of other ones. And so this is obviously a never-ending effort to bring the best resources together. I do want to mention, I said it before, but just to make it a little bit more concrete, this is how the information is conveyed to the graphical interface through what's called a JSON file. So in your distribution, if you felt like hunting for it, you're going to find a folder called KB, knowledge base. In that folder, you will find subfolders for the different areas, materials, initial crack size, and so forth, NDE. All right. And then there you'll find all the information that the GUI reads. Okay. So there's an example of what it looks like for material properties. And so you can see the title and then the numbers and so forth. So if you wanted to have your own information in your own material, you could take, say, this format, copy it over, replace it with your data, your numbers, drop it into the same KB folder, change the title of the file, of course. You wouldn't probably use the same title, right? Be whatever you want to call it. Drop that into the same KB folder, and then the GUI is automatically going to pick it up. See it, and if you select it, it will populate all the menus right in the GUI and then send that to the engine and do an analysis. It's a very nice way you can customize things. And maybe your organization wants to customize it. You'd have a whole library of these just for your organization. So that's the JSON file for it. Okay, what's the snapshot look like? Flaw size, geometry, inspections, and material properties. Those are the main four categories from which we have data here. And you can see when we get to material properties, there's quite a bit, and maybe you can see it in your software yourself. If you look onto the material icon, and you'll see for aluminum, there's 8 groups and 35 treatments. And so you can see there's lots of information. And steel, what's available, and titanium, more limited amount. If there's other materials or data sources, again, we're really open to collecting that information, combining it with what we have, and putting that back out for the public to use. All right, equivalent initial flaw size, and there's some variations on that in terms of equivalent damage flaw size or defect flaw size. So this is a mathematical construct that's been around from the 70s, and we know that it has some limitations, but it also can be used effectively. So basically, in a nutshell, one looks at failures that have been detected either in the lab or in the field, and basically grow those back to kind of have a fictitious crack size at time 0, like a material quality, right? So we know small cracks behave different than long cracks, and there's lots of things going on. We're not LEFM is not valid, for small cracks, but we're not doing analysis back here. We're really concerned about up here. So we take this information and grow it through time using LEFM to get back what we see in practice, and we do the risk assessment using this approach. Okay, so obviously the initial defect size is going to be important in almost any problem you do. So what does it look like back here? Well, it's can be controversial because how do you grow this thing backwards? How did you know what the flight profile, what the loading profile was from which you extracted this information, maybe out in the field, and so forth, right? What were the material properties to grow this back, and so on? Okay, so we understand there's maybe some controversy about this, but it is and can be effective if used for the right situations. So with that caveat, I wanted to mention that there's a number of challenges for this, and that's why this is maybe one of the harder distributions to come up with. So we've done the best we can to date, but we think this is obviously an ongoing effort. And what does one use for other materials? What does one use for 3D printed parts and so forth, right? So I'm sure that's an area of interest to many people. Okay, so again, just a caution term about use the distribution for applicants different from which the data was developed, right? So that's the caveat that we need to keep that in mind. All right, so this is what you would see in the software to date. You'll have some categories here in terms of commercial transport, military fighter, military transport, and then location, whether it be pressurized fuselage of the wing, and then where's maybe some different joints of which one's there, and then that will be used for the question.
With respect to the that's in the software, is it all self-contained or is it
It is not, it's all self-contained, yes, right. So the data that we have to date is all collected by us, combined by us, put in files, and embedded in the software. There's no active live link to any other database out there.
Follow-on question. Is this being used for
I would doubt that that's happened to date, yes, but maybe, and I don't know about it, but not that I know. Yes, but that certainly could be done. There's nothing, no reason not to do that, or it couldn't be done. So this is what we've provided to date, and you see a picture of some of what these EFS distributions look like, and you can see the information for this particular case that's sitting here. If you wanted to put in your own information, you would pick custom, and then you would put in what distribution type, and then what your parameters were, and that's what you would use for the analysis. Cracked aspect ratio, corner cracks, you may not have a 1-to-1 aspect ratio, and there's some data, although it's very limited, from T38 that's in the public domain that was extracted, and I think it's about 23 different crack size aspect ratios, if I remember right. And the average is not 1.0, it's actually skewed. It's about 1.1, I think, but it's a pretty fair variation on it from that particular data source. Okay, fastener hole offset, or sometimes called edge distance, that's can be an important one, and that's been collected from a couple of sources and then combined to come up with a distribution for that. Material sources, MMPDS was a great source. There's a number of other publications out there in Damage Tolerance Design Handbook and so forth that have been used to collect information to kind of combine that. This is what it looks like in the GUI. So, for example, for aluminum, you have the different series, the different treatments, the different orientation, and then you actually have some from thickness variations that also, if we have data on that, we also provide options to select that, and then it'll populate this information here. The version you have right now does not have any DADN variability in the database. That'll be coming up. We've got strength data to use for ultimate and yield. That's available. We put in there with normal distribution. Correct growth rate. Nathan had a nice talk, and this is the example he put together from the Verkler data showing the correlation for each one of these. So we use a bivariate normal distribution. So we'll need a correlation coefficient as well when that information comes out. POD. So I mentioned inspection is a key part of the software and part of the analysis procedure. So there's a large number of probability detection curves that have been embedded in the software that cover a number of cases. This is what this software looks like. You can see for aluminum, there's, well, obviously there's scrollable. So there's different inspection techniques, bolt hole eddy current, hand scan eddy current, and so forth. Some dye penetrant approaches. And that'll fill in the values for the probability detection curve modeled by a log normal distribution in this case. If you had already selected a material before you got to this screen, then you would not see all these other materials. You may only see aluminum if you're trying this on the software. If you already picked that material as aluminum earlier on. Okay, summary. Large amount of information collected in terms of the flaw size, the geometry. In inspections, I think there's over 100 POD curves that are available in the software. And some of them are deterministic, like you can detect the flaw of, whatever size it is for that particular inspection method. And then DADN properties that are also available. Let me stop there due to time on the database. Any questions about what's available and how to access it and how to update it with your own values? In the files, in the information you have, I put a couple JSON files in there, so you'll be able to, if you download the source material, you actually can see these from the class material. But of course, if you download the application, you'll have all of them in there. You can go look and see how they're all laid out. Okay, so I think I'll stop there.